So can you give a 1-minute overview about like who you are and what you're trying to do?
Yeah, so my name is Zaid. I've been applying to some new grad roles and I have a few interviews coming up. I just wanted to do this mock interview just to get some practice in and to see where I am and what I can improve on.
Okay, sounds good. So the first question is you're given a maze, and it's going to be like a 2D array. So there's going to be zeros, which means empty cell. Then we'll say there's going to be 1, or not 1, let's see, let's say -1, which means wall. And any other number will be gold. So basically what I want to do is I want to get, or so you're given two other inputs. So you're given start and end coordinates, and they can be a tuple, array, whatever you want. So you're given start row column, end row column. And what I want to do is maximize the amount of gold I collect and get to the end. So for example, I'll just draw the walls as X's to make it easier. So let's say we are like here, and we'll do some fake thing. So let's say the end is here, the start is here, or something like that. And let's say this is like all X's, maybe. So let's say there's like a 1 here, a 2 here, and like whatever this will be. So the empty will be the path you could take, and then maybe there's like an X here, an X here, or something, I don't know. Whatever. Something like this. And so basically the answer here would be 3 because you would just take the 1, the 2, and then get to the end.
Okay.
Okay. And if there is not, there's no way to get to the end, then return -1.
Okay, sounds good.
Okay.
Okay, so can we like go back from where we came? Like for example, here, if we put like 1 and 2 here, could we like backtrack, go towards the left here, and then come back down?
1 second. I'm going to reload this thing. I don't see your cursor moving. So basically you said like, if we go to the 1 and the 2, can we like come back? Yes, you're allowed to do that. Yes.
Okay. And then, okay, so what I'm thinking we can do is some sort of like DFS maybe, and see like start at this point here, and then we can go in any direction, see which one like takes us to the end. Or we can like get all the paths from the start to the end, and then from there we can determine which one has the max. Is that something that could work?
So if we get all this paths from the start to the end, that might be expensive, because imagine if our whole grid is like empty and you can go anywhere and it's big, it's going to be like exponential.
Yeah. Okay. So maybe. Okay, so for like this example, we just go down, and it's the only path that we can take. But for example like this, or even like this, we go left and then right and then down. So we need like some sort of backtracking within our algorithm, so to make sure that we collect everything. How can we do? Okay, so I'm thinking maybe we can start at the point S. I can do like a DFS maybe. If we get to a point that is like a dead end, then we can backtrack and go like a different route. And then we can collect, we can keep track of what we've collected during that traversal. But for the maximum amount, See, I'm having a little trouble understanding how we get the maximum amount. So if we had like a 10 here, we definitely want to go that way. But
Uh-huh.
um, I don't see how can we do that. Okay, maybe I'll just start with some.
So before you code, what would be the answer to this thing you have drawn?
This one. So we would go left, right, down, and then left, and then to the end. So it would be 19.
Okay. So you basically said like you're gonna have a DFS and you're gonna try all the different paths, right? And then you're gonna like once you hit a dead end, you'll come back and then like do more stuff. So what's the time complexity of that?
I believe it's O of n. Yeah, I believe it's O of n.
Okay. And will you revisit cells multiple times?
Yeah, we will. In this case, yeah, we will.
So if you are gonna revisit cells, how would it be O of n?
Oh, okay. So then it would be. Would it be O n squared n times n?
Um.
In the worst case, we have to like
Okay.
we go like maybe S is right next to E, and then we go all the way around to get everything, but then we have to backtrack all the way to S.
Okay. So, um, if you're going down like every path and then coming back when you hit a dead end, how is that different than what you did before? Isn't that the same as get all paths?
Yeah. So, so then would the maximum gold just be basically how much, like if there is a path from S to E, and there's gold that is reachable, then it would be the sum of all the gold that is reachable. So
Okay.
like, yeah.
And how would you figure that out?
So from here we can do, um, yeah, from here we can do a BFS, sorry, a DFS or a BFS to see which cells are reachable.
Uh-huh.
So in this example, we'll go right and down, and then we can add that to some sort of counter. And then once we reach once we've seen like every, um, yeah, like every node, like besides the end one, like even if the end is like right here, we would want to still continue downwards, right?
Hmm.
So yeah, so we're just gonna keep going until like we don't add any new nodes into our queue, and then we'll just return um, the amount from there.
Okay. And what's the time complexity of that?
Okay, so we start at node S, and then we go. Yeah, so it's gonna be n O n time. I think it's nodes and then edges. Is that right?
Well, what are nodes and edges? You have a matrix. So if it's like n times m matrix, like what can you do in terms of that? Like what is an edge? What is a node?
Yeah, so a node is just like the number of elements in our whole graph,
Uh-huh.
and then the edge are going to be the like adjacent points to each node. So each node has like the middle ones have 4, and then the edges have 2. So would that just reduce down to like O of n?
Okay. Um yeah. So let's so I think this makes sense to me.
Mm-hmm.
Um so this is n where like n is the grid, right? So
Yeah.
okay. Um so I think this makes sense. I think we can code it. I think I'm pretty happy with what you have.
Okay, cool. So let's define the input first. So you said we have zeros and empty. So I'm just going to make this a little easier. So 0, 0, 0. And then we have empty walls like 1, 1. And then we're just given the coordinates of the start and end, right? So then our
Yes.
start is, we're going to just make an array like 0, 1, and then end. Let's say the end here. So start would be here. And then we have any other integers. Okay, so let's start with that. So let's say we're going to take in a maze as well as the start and end, and we're going to return an int. Okay, so we have that. Do we have like any case where like the maze is not defined, or it's just like an empty list? Sorry, do we have a case where like the maze is not defined, like it's something just like that?
We'll say it will never be undefined, and the start and the end will always be in the dimensions of the maze. And the start
Okay.
and the end can never be a wall.
Okay, got it. So we can basically start. Okay, so we can make a helper function called DFS, and then we're going to have we're going to take an x and a y, and then we'll use the maze from the function at the top. So what this DFS is going to do is basically check where, like where we need to go, basically. So we can say if x, check the bounds of x first. So if x is less than equal to x less than the length of the maze, and do the same thing for y. And then we want to check if it's also a wall or not. So we can say x is not, or if it's equal to, or sorry, not equal to -1. And then also we want, so we start with that. And then if this is the case, then we're going to do a DFS. So we're going to say, let's have some sort of counter at the top. So we can start at 0, or let's say this is our result value. And then, so it's going to be either zeros or like any other number. So we can have 14. So we can basically just add what's at that value. So if we have a 4 here, we're just going to say res is plus equal to the maze at x and y. And then we're going to go in like the 4 cardinal directions to check, to add that to our result as well. Yeah, so we can say, okay, instead of doing it recursively, I think I'll just do it iteratively. So for this, we want a queue that's going to have our starting x and y points. And then we can have an array containing the directions that we can move. So we can say and then we can say, while we have things in our queue, we're going to basically pop from the queue. So we can say queue.pop, or this is going to be our current element, or our current xy. So current x cur y is going to be equal to the top of the queue. Then we're going to move in one of the for call and we'll go through the direction. So we'll say for I in directions, we're going to check if we'll say for, let's say next x in directions. Now we're going to check whether or not like the next point is within our bounds or if it's a wall or not. So we can say if let's say xy equal to cur y plus next, and then the same here. Now we check the bound. So if 0 and then also we want to check if x and y are not like a wall. So we can say x or maze at x y is not equal to a wall, which would be -1. So in this case, we append that new coordinate to our queue, and then we can add it to our result. So we can say I'm going to initialize our result inside, so we can say res is equal to 0. Yeah, so we can say res plus equals to what is at that point. Okay. And then at the end, once we've checked all connected components, we can say our result, or we can just return our result. We also probably want to actually yeah, so I think that could work. I think what this is going to do is go to every connected component. And the values of start and end, do we add those as well? Like if this is like a 1, like 3, should we add those as well?
Oh, what do you think?
Yeah, I think we should in this case.
Makes sense.
Right. Okay, so if that's the case, then I think this should work. And we can just start the BFS from our start and our end. And then we just return that.
Okay. Do you want to maybe walk through an example with this? Maybe you can use a smaller one than this if this is too big, or this one's fine.
Okay, sure. Let's try something like this, and then our start and end. Okay, so we're gonna start here. I'm gonna make our queue as well. We're gonna start with 0 and 1 in our queue, and then we'll
0, 1's here, by the way.
Oh, sorry. I'll just say 1, 0. Okay, so 1, 0. We're gonna start there.
Okay.
That's gonna be here, and then yeah. So we're gonna pop that from our queue. Then we're gonna go in each of the directions and check if they're in the bounds. So we start here. If we go left, that's out of bounds. If we go up, we're gonna go to we're gonna go to 0, 0. So if we go to 0, 0, it's not equal to -1. So we will add 0, 0 to our queue. And yeah, we've popped this one already, so we should remove that. This is just our current one. So we've added 0, 0, and then we can also add 2, 0 because that's not -1 and it's within our bounds. And then, yeah, so then we'll pop 2, 0. And while we're doing this, we're adding the value at that point. So here we add 1 because it's at this coordinate, and then at 0, 0, and then we pop to the next one at 2, 0. We do the same thing. We add the valid neighbors. So here, okay, so here we'll probably add back a 1. So we probably want like a visited set to make sure that we don't like re-add what we already did, right? Yeah, so we can do that. Just make a visited set. And then at each point, we can say visited.add the x and y points. And then we can just make sure that x and y is not in visited. Okay, so this makes sure that we don't repeatedly add something that we already added before. Okay, so here, yeah, so we continue going, and then we can continuously add, and then we reach the end here. Yeah. Okay, I do kind of see one problem is that like if we have a 1 here, we shouldn't be adding that because we reached the end, right?
Oh, what do you think?
Yeah, in that case, yeah, I don't think that's valid. So,
Well, you can come back, you said, right?
so if you can, like, you can cross the end and then you can come back.
Mhm.
Oh, okay, so in that case, then yeah, that would be valid.
Okay.
Yeah.
Okay. So are you good with this?
Yes. Yeah.
Okay. All right. Let's move on to the second problem. Okay. So for the second problem, you have a rate limiter, and the rate limiter is created with an interval. So I might call something like rate limiter, whatever I make it, and I'll pass in some time here. And the rate limiter takes requests from a whatever, we'll just call it a string. At a time, we'll call it an int for a request. So basically the string could be the name of the whatever person or something, doesn't really matter. And what we want to do is we want to return yes or no if this is accepted. So we can get requests from multiple different strings at different times. There are going to be some guarantees, so times will not be decreasing because it doesn't make sense, like a real rate limiter. So times will not be decreasing. And so we want to ensure that like time windows are honored. So for example, if we only want to process, so this time is like basically, let's see. Yeah, so this time is basically like, to make it simple, we'll process, actually, let me think about it. So I think we can actually take 2 inputs. We can say a time and a num requests, maybe. I think that makes more sense. So we can say that basically the time is like how long the interval should be, and then the time should be like the number of requests. So for example, time might be like 20 seconds, and number of requests might be like 20 or something. So this means every 20 seconds I can have 20 requests. So for the first 20, they'll be accepted, and then after that they won't be. So let's use a smaller number just to make it easier. So maybe time 10 seconds, we can have 1 request. So if a request comes in at time equals 1, let's say, this will say this is fine. And then until 11, we will say no. So for example, if a request comes in here, we'll say no. If a request comes in 5, we'll say no. And then maybe a request comes in not exactly 11, but it'll come in at like 20, we'll say yes. And then up until 30, we'll say no. So kind of like these are the 2 things we want to have is a time and number requests. So you want to have a constructor and you want to have a request function that we can just keep calling over and over with a string and a time.
Okay. Okay, so our time.
Yeah, so this is like a time interval that we're going to be like using our rate limiter for. And this is a like rate limit of number of requests that we can have during that time interval.
Okay, I see. And then we're assuming that times are going to be increasing. Okay.
Yeah. So we can have multiple requests at the same time, but they will never be like decreasing.
Right. And then, and we're returning. Wait, what are we returning exactly?
So just a Boolean. So you're given a string of like the person who called or whatever, the entity that called, and then the time that they called, and you just return yes or no. Will this be accepted or not with a rate limiter?
Okay, got it. And then we want to implement that in a class as well.
Yeah.
Okay, I see. So what I'm thinking is we can have some sort of, we keep track of like what is in our requests. So this is our constructor. Like the, okay. So we have, like, let's say we initialize this to 10 and 1. So every 10 we can have one request. So for this example, we will keep track of like a window. So we can say 1, 2, 5. So we'll add 1, we'll add 2 and 5, and then we can say, once we reach a point where we have, yeah, so this is, our cap is 1, so the sum of this queue has to be less than or equal to 1 for it to be valid. And then once we reach a point that's past the time interval, so here it's 20, we're going to pop the back of the list here. So we can say, we just pop that. And then the, one sec. Okay, so we're going to continue. I think we can continuously pop from the back, from the left to a point that's, to the point that's less than or equal to the top of our list. So in this case, it's 20 minus our time interval. So here's going to be 10. So we'll keep popping until that condition is true. Once it's true, then we can append this new value of 20. So to do that a little cleaner, so like for this example, we'll add 1. We'll see 2. 2 is not less than, so 2 minus our interval is
-8.
Yeah, -8, but yeah, so that's 2. Yeah, so -8 is less than the, okay, so -8 is less than something here, but I'm not 100% sure of that condition, but we'll come back to that. But then we also need to keep track of like a sum to make sure that we don't exceed the number of requests. So here we say, since we added 2, we can say that it exceeds 1 here. So 3 is greater than 1, so we can reject this one for this incoming one. And then
Wait, so Why do we get 3 and why do we have a 1 here? I'm confused.
Here?
Yeah, like how do we get 3 here?
3 is the sum of requests in the queue right now.
The sum of requests. So why would you sum them?
Because that's how many requests are within this interval.
So these are timestamps. They're not requests.
Oh,
Like,
these are okay.
yeah. So this just means you have one request that comes in at time. Like, and I assume these are all for the same person. So maybe like person A calls it here, person A calls it here. So these aren't like number of requests you get. It's just like each one of these calls will be with one request.
Okay, I see. Okay, so num request is then going to be equal to the length of our queue.
Okay.
And then, so here we said 2 minus our time. So the head of our incoming requests minus our head of our list. Is it the back of? I think it should be the back of the list. So our incoming request minus the back of the list. If it's greater than our window, then we're going to pop out the back of the list. So here we say 1, 2. Yeah, so we're
Okay.
good here.
So you're adding this into the queue and you're rejecting.
Yeah.
Okay.
Well, we're because we're rejecting because the num request is
Okay.
because of the queue is greater than, and then we can say we'll do the same thing for 5, but once we reach 20, so we'll put 20 here. We'll compare it with our thing here, so we can say 20 minus 1 is greater than 19, and then we'll continuously pop from the back of the queue. So we'll pop 1, we'll pop 2, and then we'll pop 5 as well, until our queue is empty, and then we can add 20. And then maybe after we've done that logic, we can say if the length of the queue is equal to num requests, or less than or equal to num requests, we can return true for that.
Okay. So let me ask you. So for a rate limiter window, like let's say I can have one request per 10 seconds, right?
Mhm.
So if I get a request at 1 that says yes, 2 that says no, and then I get a request, like let's change this example. Let's say I get a request at 12. What should this give you? Or not 12, let's say 11.
Okay, so here, so we start with 1 in our queue, then we add 2, and then once we get to 11, we say 11 minus the beginning of our queue is greater than or equal to 10. So we're going to pop that.
Okay.
So in this condition, we pop, and then we keep popping. So we'll say 2 here, and then we pop as well, and
So why
then
would we pop the 2?
oh, sorry, we don't pop here because this will give us 9,
Mhm.
and then we add to our queue here. So here's 11, and then we return. So the input is still 1 for this, right? Like 1.
Yes.
Yeah. So since the length of the queue is length of the queue. Yeah, so the length of the queue is greater than the number of requests. So in this case, we'll say no.
Okay. So do you think for a rate limiter, like if I'm rate limiting your requests, should I hold requests that failed against you in that rate limit?
No, probably. Yeah, probably not. No.
Okay.
So, okay, I see. So for requests that fail, um, we don't want them to be within our queue. So, So like here, we say 2 failed, right? So then we shouldn't add 2 to our queue because that's going to increase our number of requests.
Mhm.
But we should
Okay.
still, we should still reject it.
Yep. Yeah, so 11 should accept and 2 should reject.
Okay.
Yeah. Okay, so basically you're only going to add accepted requests to the queue, right?
Yeah.
Okay. And so what's the time complexity of this approach going to be, assuming you get like R requests total?
Okay, so all of our like operations for like the queue and stuff, I think those are all O of 1. So we don't have
Okay.
to keep track of those. But I think we can just like we say we get R requests in,
Mhm.
and maybe there's a case that we have to pop every single index from our queue.
Mhm.
So in the worst case, that would be R request times R.
Okay. Yeah, I think that makes sense.
Mhm.
And then what would be the average case?
The average case, we probably would just be O of R since we're not going to be popping
So
every single
per request, I guess.
per request.
Yeah, like it makes sense that like the worst case is O of R for requests because you might have to like pop everything. But what's the average case?
The average case is we're going to pop like so we're going to pop like maybe a few per request, so it's going to be like a different values. So maybe like O of R times N.
So what is N?
N is how many numbers we're popping per request.
Okay. Okay. So let's get to coding. We have about 13 minutes left, so that should be plenty of time to code it.
Sure. So let's say we have our class. And then we have our initializer. And then we can say, we can initialize the queue to just be a empty list, or we can use a dequeue. In this example, just to make like popping from the left would be a little easier for us. Then we can define our request. So we take in. Oh, also we want to add these as well. So the time interval and the number of requests. Okay, and then for our request, we're going to take in I think it's just going to be like the time, right?
So there's look what I wrote in the signature. I think I provided it. Yeah, right here, or actually right here. Wait. All right, I provided somewhere. Okay, so you're given a string and a number.
Okay, string and the number. Um,
Yeah, so the string is like the entity that called your thing.
right.
If you want to use an ID, like an int ID, totally fine. I don't really care.
Okay. So let's just say that's the ID and then our timestamp at which it comes in. Okay, so we said that the so we have our queue. So first we need to check if our if like our queue is full. So we can say if the length of self.queue. If this exceeds how many requests that we can have at one time, then we're going to have to do the algorithm of popping from the left. So, otherwise, I think we can just add to our queue. So we can say self.queue. We can just add the timestamp. Or yeah, we can add the timestamp and then we return true. Here, now we want to do a loop saying that. So we say that the beginning of the queue, so while queue, and the first value of the queue minus the incoming value, which is going to be timestamp. Should be the other way around from queue 0. This is greater than the time interval that we allow, so self.time interval. We are going to pop from the left of the queue. So we can say self.queue.pop left. And then okay, and at this point, if the length of our queue is still greater than our requests, then we fail. So here we say we return false. Otherwise, we can add that valid thing to our queue. So we can say self.queue.append timestamp and then return true.
So if the queue is bigger than the number of requests, return false. Otherwise, add it in and return true. Otherwise, oh, this is bigger. Okay. So there's one thing here that's a problem. So you're not using the ID. Maybe you could have clarified this, but so let's say I can have 10 requests, right? Look a rate limiter with 10 requests, and different people send those things. Do you think you should combine every ID into one queue?
So
because right now you're not using it. You're basically saying like, let's just take every request, combine it into one queue, and then if it's full, then like reject it. Do you think that makes sense for a rate limiter?
Oh no, that yeah, it should probably be separate for each incoming ID. So what we can do is so what we can do is have our queue actually be like a hash map of queues. So if our ID is like, I don't know, ABC, then this will have its own separate queue, and then we'll just run this algorithm on its own queue.
Okay, so can we modify the code to do that?
Yeah. So we can use a default dict here. So our key initialization is probably a little easier. Initialize it as a dict. And then we can say self queue at our ID, like each time we append. And here as well. ID. Okay. Yeah, I think that could work.
Okay. Do you want to maybe do a dry run? You can come up with your own example if you want to.
Sure. So let's just use this top one here. So we said 11 would return yes, and then 20 would return no in this example.
Okay.
So our queue looks like this, where this is the A's queue basically. And then we said 10 and 1. This is our interval and rex. Okay, so we start with A's Q. So we just add 1 to it first because we do this condition. Otherwise, we go into the other condition, and then our timestamp here is going to be 2. So while 2 minus 1 is greater than our timestamp, we pop from the left of the queue. So 2 minus 1 is great. Okay, so this condition is false, so we don't enter the while loop here. Okay, so yeah, so we don't enter the loop on the second condition, or when we put 2 in. We should want this case to return false. So we don't add it to our queue, and we say right, the time interval is 10 here. Okay, yeah, so we don't do that, and then we say if maybe we can maybe we can add like the incoming one at the beginning of this part here.
Okay.
Then we can check whether or not yeah, then in this case this condition will pass, but then we'll probably want to like remove it from our queue, so we say pop left.
Yeah,
So
I mean,
here
it's not going to run because you're not running your code, so that's fine.
so here we can say, so yeah, in this case, when we get to 2, the length of the queue is going to be 2, which is greater than our request, so we're going to return false. And then we're not going to add anything to our queue because we popped. Then we come to 11, and since since 10 or 11 minus the beginning of our queue is greater than 10, okay, so I think we should have greater than or equal to, so we can remove, we'll pop the 1. This condition doesn't pass, so we'll add it to our queue and then return true for 11. Yeah, and then once we get to 20, we can do the same thing. 20 is less than, so this is going to be 9. Yeah, so this, we don't enter the while loop. We added 20 to our loop, so we're going to return false.
Okay. Okay. So are you happy with your solution?
Yeah, I think.
Okay. All right. I think we can stop here. I think we're right at time, a minute under. So how do you think you did? What do you think you did well? What do you think you can improve in?
I think I paused a lot, so maybe just like talking a little more during those pauses. But overall, yeah, I'm not sure.
Okay. Yeah, so actually I think your communication was your best part. Like I think you didn't pause that much. I think it was pretty clear what you did. And it was pretty clear the areas you didn't know. and there was like consistent. So let me tell you what I thought.
Sure.
So for the first one, basically I would have asked a little bit more clarifying questions, like can the start and the end be a wall, and then I'll clarify if I get past an end, can I go back? I think that would have been good to do, but not the biggest deals. I think the biggest thing that consistently showed up is you didn't really understand time complexity of the things you were trying to do.
Right.
So you were like, I'm gonna get all the paths and then I'm gonna return, and I was like, so what's that? And I think you said it's like n by n or something. It would not be n by n because it'd basically be backtracking, so it'd be exponential. So it'd be like 2 to the n, 3 to the n, whatever, or yeah, it'd be like 3 to the n or something, which is significantly slower than n by n. So that wouldn't be great for like anything reasonable size. And then you basically realize, so all I have to really do is like from the starting point, I can just check all the cells and the end and like add all that up in like a BFS or something, or a DFS. And I asked you what's the time complexity of that, and you said that's n by n. So BFS is linear. You only visit every cell once because you have a visited set.
Right.
So I kept probing into this, and you kept giving me the wrong answer for something that I would consider like there's like complicated time complexity stuff, like a graph with like a Dijkstra's or something. I'd say in a BFS, it's simple enough to where you should know it. So definitely study up, like, okay, what's my algorithm? What's my time complexity exactly? And like, is it correct? Because yeah, basically, if you give like 2 or 3 algorithms and they're all wrong, then that seems like an area that you need to work in. Some thing you could do to practice for that is like when you do problems, write the time and space complexity for them afterwards, and then you can check it in like whatever, some AI thing, and make sure it's correct. But yeah, I think that's like it's okay if it's a little off, but if you're like off in every single section, then that's going to be like a red flag. So I thought that was like the worst part. But the other thing that is okay, but typically you want to avoid, is you said, I'm going to do a DFS. And then as you were coding, you were like, oh, actually, I'm going to do a BFS.
Okay. Yeah.
And so it makes sense to do it if you realize, well, ideally, actually. So basically the reason you don't want to pivot, like almost always, is because the only time you should really pivot is like if you know your solution doesn't work, right? You're like, I wrote something down and then I pivot, and it's because I realized my first solution didn't work. And then I can kind of say like, well, maybe you should have planned it out a little bit better and then made sure it worked before coding, right? So basically in almost any situation, you shouldn't pivot ideally. This problem can be done with either. So you could have done DFS. I don't know if you're like more comfortable with one or the other. Generally, if you know it can be done, so ideally you basically realize this can be done with either. And then you just pick the one you're more comfortable with and you stick to it. I think that would be like for me, for example, I'm more comfortable with BFS. So I would just say like, I'll just do BFS. Either one works. Yeah. And then you had some bugs and you fixed it in the test. Ideally, you fix it in like the actual code. So for example, for the BFS, you notice you didn't have a visited set. That's like a pretty big part of a BFS. And ideally, you shouldn't have to get to the test part to realize you have that missing.
Right.
And then also that end thing where you were like, oh, if I get to the end, I'm at the end, then I shouldn't do stuff like that type of stuff. You should have it all clarified in the beginning, ideally, right? You don't want to like come to an edge case like 20 minutes in and be like, what should I do in this case? You want to be proactively like thinking about these things, and that would have been better. And then you still had some bugs at the end. So one bug you had, for example, is you append to a visited set, but you never appended your starting cell to the visited set. So like you'll have a starting cell, you'll go to all the directions, you'll go everywhere, but then you'll basically revisit your starting cell twice, which I think is like minor. It's not the worst. And then, oh yeah, the bigger bug was you never actually checked if you got to the end. Like you just did a BFS and returned the sum. So I think that's like a critical bug where it's not a syntax, it's not small, it's like you just return a sum where the maze was unsolvable. Does that make sense?
Okay. Yeah. Yeah.
Yeah, I understood that correctly, right? Like you never really checked if like you got there. So you should have basically done a BFS and then just check, did I get to the end? And then if so, then you return the total. If not, and it's not a hard thing, but like I basically characterize bugs and like, okay, small syntax error here or there, fine. You forget to do some small thing here. If it's like a critical like path that you just didn't cover, I'd say that like that's not good. So because of all these things combined, basically I ranked your communication, your speed actually pretty good, but you had a lot of mistakes, and ideally, and your testing didn't catch that you never visited the end.
Yeah.
And so I would say this would be like a lean no hire. But the good thing is like most of these things that you were weak in are like fairly easily solvable. Like basically just clarify constraints and like test better and then have a good understanding of time complexity. That just comes with like do enough problems, write down time complexity, and over you'll get like a very good understanding. And then ideally with time complexity in space, you want to define what variables you're saying. So a lot of people like you might have 3 inputs here, like you might have like a maze, you might have like edges, you might have whatever, and people will just say like, oh, it's O of n, but like what is n? So ideally you clearly say like, so like if my maze is n by m or whatever, then like my time complexity is O of n by m and so on. So it's very clear that you know what you're doing. And the best thing you could do is you can go through line by line. You could say like, so this section is this section is this section is this, and then I know you have like a very clear understanding of like time complexity and space complexity. So you could do that before you code. So you could say like, here's my plan. This part's going to be this part's going to be this part's going to be this. That's time complexity. And you can talk about these things as you bring up your algorithm. So ideally, the best thing you could have done was like, okay, so I'm going to try every path. Oh wait, that's going to be exponential. So let me see if there's something better. Oh, I'm going to do a BFS. BFS is going to be linear, so that's going to be better. And like you do as much stuff proactively without me telling you, and you don't want me to like find edge cases for you. So I basically wasn't sure. Like I could be like, so you wrote this line wrong, can you fix it? But I feel like that's not the best. Like ideally you want to find that stuff yourself. Okay. So for the second one, let's see. So yeah, so definitely I would have clarified what to do because you came up with like the wrong implementation of the rate limiter. Like you basically clarified you stored failed requests as like a rate limiting. If you don't know, I would clarify. So I'd say like, okay, so if a request passes, like that limits, but what if a request fails? Should that rate limit the rest? And I think it's like pretty bad if you have a solution that just like, I mean, that works like not like a normal rate limiter, because a normal rate limiter doesn't actually like block like on failed requests. It wouldn't make sense. But if you don't know, still clarify that stuff. So any kind of that thing, clarify. So the two things that you kind of weren't sure that you did wrong was you combined all requests into one queue, and I would have clarified that. Would have said like, so that you have this rate limiter, but is this rate limiter like global, or is it per like person who calls? And then how do I handle failed requests? Like, do they block more, or do they count as like nothing? Even if you know what a rate limiter actually looks like, because maybe like the one I'm trying to have you make isn't what an actual rate limiter does. It's good to clarify these things, because then your code is like to what I would have expected. Because what I would have expected was you separate them out, and then for failed requests you don't include those things. And I could have been more specific, but honestly I feel like it's pretty good for me to be vague and you clarify these things. Yeah. So then so you used a queue, and then you were using all requests because I think you just because you just thought like it was the other thing. So I would have clarified that. And then I basically had to tell you like, so what should happen in this case? And you were like, oh, it should be this. And I'm like, no, it actually should be this. So that's where like you being proactive would have been good. And then I think you said the time complex. Oh yeah, I remember. So you said the time complexity. I was like, what's the time complexity of worst case? And you said it's like O of n or O of r, because like I'm gonna have to pulp everything. But the average case would actually be O of 1, because if you have n requests, right? So you have n requests total, and every request adds one item to the queue. Then your average time complexity is basically like one pop or one push, one pop per request. So the average case would have been O of 1. So you said it's like O of n, where like the number of items have to pop. So it's good to understand that as well. It's a little bit deeper, but like amortized time complexity, like what's the average case? So if you have like n stack pushes and you have n requests, then it would just be O of 1. So that would have been good to know as well. And then so I basically wrote your bugs was you combined all users into one queue. Shouldn't be the case. Should have clarified this. Because I definitely don't expect you to know like how rate limiter works or whatever. I think that's totally fine. But if you don't, then you should definitely clarify. You also had a bug. Oh yeah, so you actually had a bug, and then you ran through your code, and then you actually made it like worse. I feel like so you like appended the request, and then you pop. So first of all, there's a couple things here. Like you can't pop left from a list because you have a queue but use the list. So you can't pop left from a list. So these should be queues.
Oh, yeah.
And then the fix would have been not this, but it would have just been. So if it's like while you have a queue, you do the pop. So ideally this is a queue, and then pop left works. Then you basically say if it's greater than or equal to, you just return false, and then you do your append like you had here,
Oh,
because
yeah.
So basically you just pop everything that's extra, and then you just check is there space.
Mhm.
Yeah, and then that would have been fine basically. So because there was like consistent problems in the same areas, like time complexity, not looking at edge cases, bugs in your code, I would say this would be like a lean no hire
Mhm.
for like even for like I'd say like a tech screen, because I don't think these were like, I mean, you can tell me, I don't think these were like hard questions. I don't think there were any complicated algorithms, but you had
Yeah.
consistent like fundamental knowledge gaps, which was like pretty important, but luckily they're like pretty fixable as well.
Mhm.
So basically if you don't think of edge case, or if you don't cover requirements and your solution just completely wrong, that's just like an auto fail.
Yeah.
And then the same thing with like covering edge cases and being able to test and walk through your own like mistakes. Um, so yeah, I'd say for like, lower like intern whatever or like tech screen type stuff, I would definitely focus on easier problems like this, but to make sure you're super clean and like covering all the edge cases, your code's really good, your time and space complexity is like really solid, really get your like fundamentals down. And then
Mhm.
if you want, you can do like harder problems. But a lot of people like do harder problems or do too many things, and then they're like super shallow knowledge and like everything, and then it turns out to be a disaster. So I
Right.
think basically, yeah, just I would stick to like this level problem. Just make sure you really know your like fundamentals, and then you can basically do like harder stuff from there. Uh,
Okay.
yeah. So does that make sense? Curious what you think about like these problems. You think this is like pretty reasonable?
Yeah, I think this is like, yeah, it's pretty good.
Okay. Well, cool. Yeah. So if you don't have any other questions, you can book another one if you want to. I basically just ask people not to book in like the same month because I'm like full for like forever.
Yeah.
So if you want to book in the future, feel free.
Sure.
Okay. Cool. See ya.
Thanks for taking the interview.
Yep. No problem.
Thanks. Bye.
Bye.